So we've talked about constant acceleration rotation, but we kind of sidestepped constant velocity rotation. And that's a special class of motion that we call uniform circular motion. So again, what I'm intending here is for omega to equal a constant, of course. So omega is constant, meaning alpha is 0. So let's think about this. Let me move my circle a little bit. So we have constant angular speed. So let's draw an object on this motion. Here's a dotted line. What's my object? I don't know. Green circle. Perfect. And let's let it move, up to, like, say here. It'll do that in some amount of time. This is some, like, radius. And there's a tangential velocity at each point, right? So there's a tangential velocity here. That's like v initial. And there's a tangential velocity here. That's like v final. So let me ask this. What is the acceleration of that object? Well, I said alpha is 0. Right, but alpha is an angular acceleration, which also means the tangential acceleration is 0. But what about some kind of radial acceleration? Am I accelerating in or out in any way? Well, at first glance, we say, well, acceleration is delta v over delta t, and v is constant, right? No. V has a constant size, but it is changing direction. Remember that acceleration is a vector equation, right? Acceleration is delta v vector. What is delta v vector? It's v final minus v initial. Okay. And again, if these were just sizes, those would subtract to 0 because v final and v initial have the same length, but they have different directions. So we've done vector math, so we can ask, what is the direction of delta v? Well, okay, we can do that. V final is, let's draw that. V final points off at an angle like this. There's v final. And I'm adding negative v initial, so negative v initial points straight down, because v initial points straight up. So that's like this. So there's minus v initial. And the vector that connects those two is like right here. That's delta v. That, it put on my diagram, I didn't draw that very well, put on my diagram, it points basically this way. I can do better. Radially inward. So it turns out, again, delta v is the direction of acceleration. So objects in circular motion are accelerating toward the center of the circle. We call that acceleration centripetal acceleration. Let's write that over here. Centripetal acceleration. Sometimes we use A sub c. This is the acceleration that causes circular motion. All right, it is perpendicular to the velocity at any point. So I drew on this figure 2 time points that are kind of far apart, but if you draw those time points really close together, you can see that the acceleration, acceleration is radially inward, right? And the velocity is always tangent to the path. So velocity and tangential velocity and centripetal acceleration are always perpendicular. So that makes sense, actually. Um, if we have a velocity vector, right? If we have a velocity vector this way, and acceleration, say, this way, that acceleration does not cause the velocity to get bigger or smaller, because if it were pointing a little forward, right? If we're pointing this way a little bit, it would cause it to get bigger. If it were pointing this way a little bit, it would cause it to get smaller. But if it's pointing at a right angle to it, all it can do is turn that velocity. It's just exactly what circular motion is. It's just turning velocity vector. Okay. Fabulous. How big is that centripetal acceleration? There should be a number for it, right? How do I calculate the size of centripetal acceleration? Well, we're halfway there. So I have an isosceles triangle here. It almost looks equilateral, but it's not. So this is isosceles, right? V final and V initial are the same length. Delta V is some different length. There's another isosceles triangle, which is right here. All right, where I have R there and R on the other side. Let me redraw it. So here, there's R. There's the other R. I should draw that a little more true to life. So one of the R's is this way. The other R is a little higher like this. So there's R. There's R. And this is the arc length, basically. Right? Again, arc length is actually the curvy bit. But if this is small, if we use a really small theta, then S and the actual side of that are pretty much the same thing. Okay, so here's what I want to say. These two triangles are similar. I didn't draw them super close to scale, but what I mean by similar is they have the same angles. All right, so I can write the short side divided by one of the longer sides equals the short side divided by one of the longer sides. And I'm going to write that V, instead of V final or V initial, they're both the same length, I'm just going to call them V. So this is a magnitude equation, so the distinction between final and initial doesn't matter. Okay. Okay, great. What if I multiply both sides by 1 over delta t? And you might ask, why would you bother doing that? I have a reason. I do, I really do. Because S over delta t, let me kind of highlight it. S over delta t, that's just V. And delta V over delta t, that's just A. Right? Okay. So we can do another line. We can say V over R equals A over V. So I can multiply by that V, and what I get is A equals V squared over R. That is the centripetal acceleration. So that is how we can get mathematically how big that acceleration is. Okay, does this make sense? Think about forces that cause circular motion. Let's imagine you have a bucket on a rope, and you're swinging it around in a circle. In a plane that's horizontal, right? Meaning a plane that's parallel to the ground. So you're swinging this thing around. If you want to swing faster, you have to pull harder, right? It's harder to hold on to that rope. That's because the required centripetal acceleration is bigger because V is getting bigger, right? The other thing you can say is if you want this to travel in a smaller circle, so if R gets smaller, you also have to hold a little tighter, meaning the force causing centripetal acceleration has to get bigger. Okay, let's do an actual example. And in fact, the example I have is exactly that. A bucket being swung in a horizontal circle. So we can draw a picture of this from above. So let's see. Here's this. There's that. and there's the bucket. And it's traveling in this circle right here. I can do a little better than that. Okay, that's pretty okay. So I've got some radius for this circle. I could label it with a green. There's a radius. Let's have it going this way. So there's a tangential speed, and it must be accelerating this way, a sub c. And what do we have? We know that the radius is 1 meter, and the rate is 100 RPM. And again, an RPM is an angular speed, so that's omega. And I know immediately I'm going to need that in radians per second. So let's multiply by 2 pi to get it in radians and divide by 60 to get it in per seconds. So that turns out to be 10.472 radians per second. Okay. So the question is, what is the tension in the string? Okay. So let's draw a free body diagram, and we're going to draw it in the XY plane here. So there is gravity on this bucket. We're going to ignore it for now. Technically you can't, but if this tension is big compared to the weight of the bucket, it's negligible, the error that we're introducing. So we could draw a free body diagram. There's the y direction. There's the x direction. And what forces are acting here? What forces are acting? Well, it's tension, right? There's tension. And you could ask, what about centripetal force? And I would say, centripetal force. I wouldn't say centripetal force. I wouldn't say that word. Because that makes it sound like there's a special force that's different from what we've already talked about. There is centripetal acceleration, and all accelerations are caused by forces. But a force causing circular motion is just a force that we've talked about. In this case, tension is causing circular motion. All right, so if you must label a centripetal force, tension in this case is the centripetal force. But I think it's confusing to say centripetal force in the first place, so I'll stop saying it. So the only things that can show up on my free body diagram are actual forces. I've got tension. And again, technically, if I drew this from the side, I would have gravity as well. And so tension would have to act up a little bit in the against gravity direction. But let's ignore that for now. If this tension is high enough, if I'm swinging this fast enough, it's not going to dip too far. Okay, so let's write F equals ma. Right, we filled out a free body diagram. The next step is always a Newton's second law. So the sum of the forces, we'll say in the x direction, equals m times a sub x. Okay, so the only force is tension, and it's to the left as I've drawn it. So I could say tension minus tension equals mass times a. What is a? Well, it's centripetal, right? Right, because this object is going in a circle, so it has some centripetal acceleration. Great. So let's write another line for this. Minus t equals m. Remember, centripetal acceleration is v squared over r. And in this case, it's to the left, so I'm going to put that negative sign in. Minus v squared over r. Again, the negative sign is not in the definition for centripetal acceleration. I'm just saying, from my picture, I know it points to the left. And I know left is negative. So, okay. So that gives me this, that tension equals m v squared over r. And I think I know all those numbers. I think the bucket's 50 grams, and the radius is a meter, and v, I don't know v, but I know omega, right? So let's do that up here. Let's say v is omega times r, and omega is 10.472 radians per second times 1 meter. So that's 10.472 meters per second. You see that? Okay, so we use the radius of 1 meter to change the unit on V. Alrighty, so we're almost there. The mass here is 50 grams, so that's 0.5 kilograms. Sorry, that's 0.05 kilograms. Times V, which is 10.472 meters per second, squared, all divided by the radius 1 meter. So that gets me a number. It's 5.5 newtons. Great. Great. Let me mention this. There's another definition for centripetal acceleration. Centripetal acceleration, the magnitude is v squared over r. But remember, we just said this up here, that v equals omega r. So I could plug in omega r squared divided by r. And then one of those r's goes away. So I get omega squared times r. So that's just another way to calculate it. So we didn't have to convert omega to v here. We could have left omega as omega and used this other equation. We get the same answer. It doesn't matter what you do. Okay, great. So you have a bucket on a string. What's the next thing you're going to do with it? Well, you're going to swing it in a vertical circle, right? So instead of swinging it around you, you're going to swing it up and down. That's example 4. Take that same bucket, and now we're going to swing it in a vertical circle at a different rate. So let's draw the picture. We've got the bucket. Let's draw it at maybe a couple different points in the path. So there's the top, and there's the rest of the circle, more or less. There's the bottom, and maybe off to the side. Just different time points in here. Again, same radius as before. It's a different rate now. It's 60 RPM. But it's the same 50 grams, and it's the same meter radius. The acceleration, the centripetal acceleration, is still radially inward at every point in the path, always at a right angle to velocity. So let's let it go this way. And again, the size of velocity is not changing, it's just the direction. So I want to know, what is the tension in the rope at the top and the bottom of the path? These are the two kind of critical points. Really, the top of the path is the most critical point. The sides are a little more complicated to deal with because gravity's up and down, but the net force needs to be right or left. So let's consider the top first. So for the top, we could draw a free body diagram for this. So there's my y direction, and there are two forces here, right? There's tension, which acts downward, and there is weight, which also acts downward. Right, and I can now write Newton's second law for this. The sum of the forces in the y direction equals m times a sub y. Okay. So what are the forces? There's tension and there's weight, and they both act downward. So I'll say minus tension minus weight equals mass times centripetal acceleration. Okay, so here is an example of when we ask what force causes centripetal acceleration. Well, at this point, it's actually two forces, right? Tension and weight both act together to cause this bucket at the top of the path to accelerate centripetally. So I can't identify one centripetal force here. It's really a net force causing centripetal acceleration, which is why I don't say the word centripetal force. We just think centripetal acceleration, and it must be caused by a net force. Okay, so we can plug into this. We can say minus tension, that's what we're solving for, minus mg equals m times The centripetal acceleration here is v squared over r, and I'm going to put in that negative sign just to reflect the direction that the centripetal acceleration is. Right at the top of the path, that net acceleration is downward, radially inward, which makes sense because it's caused by two downward forces. There's no way for this to point any other direction than down. Okay, so we can do this math. What are we doing? Let's see. I can make all the signs go away. I can subtract mg to the other side, so I can say t equals mv squared over r minus mg. It is tempting here to note that you could factor out the m and say v squared over r, that was centripetal acceleration, and g is acceleration due to gravity. It's tempting to think of this problem from the beginning as a difference of a centripetal acceleration and g. I promise you that's more of a headache than it's worth. It feels like a shortcut, but it's too easy to screw that up. Whereas if you start with Newton's second law, it's much more difficult to screw that up. Just a word of advice, word of caution, really. Okay, so at this point we can plug some numbers in. So 50 grams, 0.05 kilograms times 1 meter per second squared. Is that one? Nope, that's wrong. We're swinging at 60 RPM, right? 60 RPM turns out to be 6.28 radians per second. And then we could get a velocity out of that. Actually, let's use omega. I'll show you that here. So 60 RPM, that's omega, equals 60 RPM. And as we have before, if you multiply by 2 pi and divide by 60, in this case you get exactly 2 pi, which is 6.28. That's radians per second. And we can write centripetal acceleration as omega squared times r, so that's what I'm going to do here. Omega squared times r. So that's 6.28 radians per second squared times r, which is 1 meter in this case, minus 0.05 kilograms times 9.8. And what I get for this tension when you do that is about 1.5 newtons. Okay. Okay, that's the top. What about the bottom? What about the bottom? Well, okay. For the bottom of this path, two things change. Right? We can draw the free body diagram for this. You know what? Let's move over. That's not what I want. Let's move over here, so I have some room to fill out Newton's second law. So what are the forces acting? Well, there's still gravity and there's still tension. Gravity acts down, and tension acts upward. Right? Okay, so there's one change. Tension changed direction. What about Newton's second law? Let's move this like here. Okay, so the sum of the forces in the y direction equals ma sub y. So tension minus weight, because tension is now up, so that's one of the changes, equals m times centripetal acceleration. The other change is that centripetal acceleration now points upward. So we can go tension minus mg equals m times v squared over r. Or, again, it might be useful here to use omega squared r, so we don't actually have to calculate v. Okay, so acceleration is now the opposite direction. It's up instead of down. So two signs changed. Right? And so what's the net effect? Well, we add mg to the other side, and I get t equals m omega squared r plus mg. There's the big difference. Previously, in the previous part at the top, I had minus mg. Now I have plus mg. All right? Okay, so if you plug into that, 0.05 times 6.28 squared times 1 plus 0.05 times about 10. What I get for this is about 2.5 newtons. Okay, so why is the tension higher at the bottom than the top? Well, at the top, gravity was helping. At the bottom, gravity is working against centripetal acceleration. So tension has to not only match the weight, it has to supply enough extra force to also cause centripetal acceleration. All right, so again, you can ask at the bottom, which force is causing this to go in a circle? And the answer is, well, part of tension, right? Tension is doing two things. Again, it's offsetting weight, and it's also causing circular motion. So I guess at the bottom this has a more clear answer. Tension is causing circular motion, and the weight is actually working against you. But at the top, they're actually working together. So we'll see lots more examples, but again, they all follow the same sort of procedure where you draw a picture. You can label centripetal acceleration because that helps to see that on the picture. Draw a free body diagram, fill out Newton's second law, and remember that the acceleration in the radially inward direction is centripetal. It's v squared over r. Otherwise, it's very similar to what we saw in chapter 4. So we'll see more of these.